Okay, let's begin. Welcome back, folks. We survived our second exam. Congratulations on getting through that one. And now we're moving in through strong induction for our last class before entering spring break. Seems like this is the hardest class to really attend for a lot of reasons. It's easy to be tired after exam, and it's easy to not make it to a class right before spring break. I remember missing out on my classes a lot when it was right before spring break as well as a student. So I appreciate you all making it in here today. Well, any questions at all to start us out? Okay. Well, aside from the announcements we see here, just some extra information. I'm going to be posting your solution to your homework assignments first, then moving over to grading exam two. That way, after exam two is graded, you'll have a really good understanding of what your current standing is on the course. If you took exam two in a testing center, I'm just going to email it right back to you, same as exam one. If you took it in the classroom though, and you just want it back sooner because it's going to be a long break, don't hesitate to email. I'm happy to scan it and directly email it back to you. After I get through all the grading, I'll be coming back to this location here on Moodle just to post some basic summary statistics, the solution to the exam if you're curious. And I think that's it for my announcements. Even though we don't have any classes on spring break and we don't have any announcements, or excuse me, any office hours, I'm still checking my email every morning. That's pretty much what I do just as a routine habit. So if you do have questions at any point, don't hesitate to email. I'll definitely get to your question sometime, definitely in the morning if possible, or if I'm just next to the computer at some time during spring break, maybe sooner. But I think that's it for my announcements. We're going to do another topic on induction, strong induction you see here. I moved this link for R and RStudio down below, since it's kind of fun when you write down pseudocode to just test it out to see if it works. Feel free to use whichever programming language you'd prefer. I like this one because it's a pretty basic language. It's fast, easy to run, and the RStudio gives us good code completion at the same time. But I think that's it for the announcements. Let's jump to the top of the document, strong induction. Another wall of text to get through, but let's organize by first starting right here. Even though we're in a new section on strong induction, I felt like we should say what is ordinary induction. This is the author's wording right here. Proof by weak induction is what he now calls it, now that we're in this section. Feels kind of rude. It's not that this method is weak. It just has its own limitations. So to tell between when you're using proof by strong induction versus proof by ordinary induction, or if you prefer to say weak induction, really the major thing is what you're doing right over here. There's a whole category of problems where that just isn't good enough. The prior case involving the next case. We're going to be looking into a class of those specific problems. What we sometimes need is more than just one prior case assumed true. We might need the prior case and the case right before that one to be assumed as true in order to prove the nth case is true itself. So that's the idea with strong induction. If this isn't enough for us to prove the implication, if we need more conditions, then we're in this technique right here. Even if we only need a couple extra conditions, this one is just saying one additional condition, the full case says, here's how it works. Take the prior condition and every one's, including the base case from the first step up here, take all of those, assume them true, which is natural to do right here because you've already shown it's true. Notice that these are ands as well. That means when you assume this part is true, the hypothesis and implication, you're assuming the prior one, just like we did in ordinary induction. You're assuming the one before that, Pn minus 2 as well, and then all the way down the line. You might not use all of those assumptions there, that every one of those are true, but it allows you to extend what we did above, give us extra information if we need it. So that's the whole idea with proof by strong induction. To get a real good feel for how this goes, it very quickly pivots on our understanding of ordinary induction itself. Any questions, folks, about ordinary induction or strong induction before we give it a try? Okay, Well, let's give this one a go. Example 1 says, conjecture a formula for AN. That seems kind of rude in a way, right? When we did induction problems in the prior section, they always looked like this. Here's a statement. Now go and prove it. That was the whole idea. Every single problem looked like that. Here's another statement. Now just go and prove that one. This one is saying we have a sequence. It's an infinite sequence. We have two starting values. An initial value, the very first term of the sequence, is going to be 1. The very next term of the sequence will be 4. And then we recursively define all prior terms right after, starting at 3 and going forward. We're taking this combination plus 2 of the prior term, the term right before the prior term, I need a good word for that, to produce the next term, a sub n. This kind of recursion comes up all the time in mathematics. In Calculus 1 itself, if you look into Newton's method for approximating a solution to an equation, it is a recursive formula itself. So here we're conjecturing a formula for AN, we're producing our own formula, then we'll prove it using strong induction. How do you come up with the formula for this? Well, it's when we say conjecture, it's kind of a way of saying we're going to write some stuff down and make a guess. So it's going to be a really fancy guess, a well-informed one, and then we'll prove it's more than a guess by running it through strong induction. So let's write out a list on the left. A1 is 1, A2 is 4, and this feels almost unfair and kind of nasty in a way, but keep in mind, humans are really, really good at pattern recognition. Give this a try, just play around with the numbers. You might already see a pattern right here, right now, just from the very first two. But to make this pattern a little bit more concrete, good idea is to calculate several more. Let's do at least 2 more, maybe 3 more. Computation of A3 is something we should do either way, right? If we're talking about a recursively defined sequence or any structure defined recursively, here's the recursion right here. We should work with it a little bit just to get a feel for what's new in this problem. So to compute A3, we use A2 is what this part is saying, and A1 is what this part is saying. It reveals why we had to have 2 initial values for this kind of structure. So we'll go 2A2 minus A1 plus 2. Idea being if it's A3, this is A2, and this is A1. But then once we get here, we pull in the other information. A2 is 4, minus A1 is minus 1, plus 2. So we get a value of 9. Must have been a really long week for me so far. Arithmetic is a little slow, but let me know if the arithmetic goes bad at any point. So we've got a 149. Anyone see a pattern emerge so far? If not, no worries. The good call here on the next step is the more data we have, the more the pattern is just going to jump at you. So let's do A4 next. A4 is going to involve A3 and A2. So let's go and write A4 is 2A3, just carefully writing out the formula, minus A2 plus 2. So it's going to be 2 times this value minus that value, add 2. So that's going to be 18 plus 2 minus 4. Looks like a 16 on this one. So A4 on this comes out as 16. And still, we can do a whole lot more, but anyone see a pattern at this point?
Is it adding by each odd number going up?
Not
So,
quite. What you're saying, this is plus 3. This is plus 5.
huh.
This is plus 7, right? Yeah, that's an interesting pattern. So it's adding the next sequential odd number each time. I never even saw that pattern. That's a good one to suggest. Let's write out A5 and see if it carries through. Thanks for suggesting that pattern there, Michael. So the pattern carries through. Here's our check next. add 9, right? So we should be at 25. So if we go A5, it's going to be twice A4, which is 16. Then it's going to be minus A3, which is 9. Actually, let me write this in just so I don't grab the wrong values on accident. Twice A4, that makes it a little bit clearer, minus A3 plus 2 will become twice 16 minus 9 plus 2, which is now 32 plus 2. So we're up to 36 minus 9, exactly 25, just as you predicted. So we've got a 25 on this one. It looks like this pattern actually holds through. On this last one, it was plus 9. Does that make sense to folks so far? Okay, the pattern I was personally thinking about, this is why these problems can be really fun, is that everyone has a different take when you see the same kind of problem. The other pattern I was thinking about is A1 is 1 squared, A2 is 2 squared, A3 is 3 squared, and so on is our pattern. Just building out the sequence here of the squares. But it looks like we could also think of it as just adding the sequential odd numbers going down the line. So we've got two competing formulas for AN. The conjectured formula for AN is either going to be, let's use Michael's approach first, AN equals, we're going to encapsulate this pattern as the nth term of a sequence that was defined recursively. How should we start? Maybe begin by putting in the initial value, right? AN plus 1 plus, now we're adding sequentially higher and higher odd numbers, right? How should we write that in as a formula? Well, we know an odd number is going to be something along the lines of 2n plus 1. So that's going to give us all of the odds down the line once we go to add this in. So when n is 1, let's see here, we'd be a little bit too high, right? So how about we add in front of this? We need something in front so that when n is 1, we just get this term. How about n minus 1? Kind of just spitballing here, try to come up with a pattern. Does that look all right to folks for just an early try on it? Okay, we might make some adjustments on this, but here's the next thing we're doing. When we are conjecturing a formula, we're looking at this pattern down here. Now that we have a formula down, we have to double check. Does the formula match the pattern? If it doesn't, we'll make some fine-tuning adjustments to it. If it does, we're on our way. We move over to part B and prove this is the right way to define the recursive sequence if we wanted to explicitly as one formula, just giving the nth term itself. But let's do the test right here. So A1, using the formula on the red dot, we'll place a 1 right there. So we do get a 1 out. That's encouraging. A2, if we plug 2 right there, we have a 1. So 2 goes into this location. It's going to be 1 plus 5 for value 6. Not quite there, right? We're trying to hit a 4. Some adjustments have to be made here. Kind of tough. I'm not quite seeing the solution by analyzing the sequential odds on it. Anyone have a suggestion for another way to try to modify this one?
It would take me a lot of time to figure that out. So how about we do the square one like you suggested, Professor?
We could totally do that. There's got to be a way to do it though, because it looks like this is a bona fide legitimate pattern. Sure, I never checked A6, but starting to think it should really pan out. And even if it didn't check at A6, based off this information up here, even still, this is a legitimate sequence, right? We should be able to come up with a pattern that generates the same kind of structure. Add 11 on the next one, for example, to get 36. But going with a second suggestion, let's give it that approach.
I kind of have a question about that.
Yeah, go ahead.
So In our definition in the top, it says from n equals 1 to infinity.
Oh, yeah, right
So
up here.
on A1, when we try to do n minus 1, does that mess with anything?
Uh, I see what you
Because
mean.
we'd be trying to do A of 0, which doesn't seem to be defined in the sequence.
Yeah, that would be a total undefined. You're absolutely correct. So this part right here also includes the information. It's only a valid formula for the next terms if n starts out at 3 itself. So this should have been kind of like bracketed together. Does that tie together the question you were asking about?
Yeah, I think so.
Gotcha. So yeah, we'd start at A1, we'd start at A2, and this formula only becomes valid when we're dealing with A3 and so on, all the higher indices. So at 3, this is the one spot where we're okay here, and the other spot where we're also okay, only because it's starting off at 3. If we put, just like you said, start at 2, now we've got a big problem. Well, the whole question is just undefined, ill-defined. We don't even have a sequence any longer. Other questions about that so far? Or other related questions? Okay. Again, thanks for suggesting that other interesting pattern, Michael, about increasing the odd and just sequentially building these out. That's another interesting way to look into this problem. But as you suggested, let's think of it as AN. Let's write down here, just to tie together this fancy new word, our conjecture, fancy word for a guess. Let's make it a verb. We conjecture that AN equals n squared. Because when we look at this list, 1 can be rewritten as 1 squared or as 2 squared. And what we're trying to do is look at the index and the base to try to match it up to really see that pattern. This one is, in fact, 3 squared down below, 4 squared on this one, 5 squared on this one. And so it seems plausible it should be n squared for everything. Kind of wild in a way, right? It starts at 1, next term is 4, and this interesting linear combination, add 2, of the prior two terms is another way to just say, list out all the squared numbers. A fantastically complicated way to say that. Or is it? That's what part B is all about. Prove it's really true by proving your conjecture using strong induction. Well, any questions at all, folks, before we go to the next phase of the problem? Okay, so we're about to prove the nth term of this recursive sequence is just n squared. It can be simplified majorly is what this is all saying. But the next question you might have is, why strong induction? Well, that's something we should address right here now before we just launch into some random new technique. Strong induction might have been indicated because of this feature of the problem. It involves a prior term, and if that's all involves, this would have worked right up here. You'd have been all set to just get going and prove it by a regular induction. But the moment they added a second term, now we've got a problem. This just isn't going to work anymore for us because this is going to involve an inductive hypothesis that involves both Pn minus 1. And let me just do a really quick design change here. Usually that works. Let's put in Pn minus 2 here. Because of the a n minus 2 in the recursive sequence, we need Pn minus 2 for this one, and we need a statement about Pn minus 1 for that one there. So the recursion involving 2 prior terms is the only reason we're doing strong induction in this whole problem. And let's really make that firm by taking this whole thing right here, and let's carry it down as we work through strong induction. It starts off exactly the same as before. There's a base case. But keep in mind when the author wrote this statement here, he was trying to write it as general as possible. We do have to fine tune things occasionally because we start at 1 per this sequence. We're not starting at 0. And sure, we could re-index a whole sequence if you prefer to make it start at 0, but that seems like a lot of extra complication. Instead, down below, we're just going to make an adjustment that goes like this. Prove the base case, which is going to be P1. Let me say it this way. We'll prove P1 is true. Then the inductive case, we're going to assume all of this is true, but it's going to start at n greater than or equal to 2. And this one will be a 1 and a 2. Let's see here. And then it does go all the way up to the Pn minus 1. So those are the adjustments we would make if we start right at the index 1. Let's now maybe go down a page. And, well, maybe before we go down a page, let's say what we're proving. That might be a good device. We're proving that this predicate function P of n is always going to evaluate to true. P of n is the statement that an equals n squared. And just as a reminder, this is going all the way back to chapter 3. This isn't saying what the function does. This just tells us the predicate function is a Boolean valued function, and the Boolean is given once we do a check here if it's true or false. So once we define that by the red dot, we have a mathematical function that goes from, notice the dual use of colons. Colon here is just to say such that, this statement. P is here as a colon, a little bit closer to P to say it's a mapping that starts at the positive integers, so z greater than or equal to 1, and goes to the set of Booleans, true, false. So that's what P is as an honest function. This is a statement we want to prove, but the thing that we're actually proving with strong induction is a quantified statement. So we can say, we will prove that for all n and z greater than or equal to 1, P of n holds as true. And this is the most compact way to write it. For all n and z, P of n. But if you want to be really explicit of what P of n or the mapping P is itself, that's a function that's Boolean valued because that's its codomain. You might want to be a little bit more explicit and say P of n equals true. True with equality here in the literal mathematical function notation sense. It'll always evaluate to true for every possible integer n. In the last section, we always wrote it this way. In this section, let's change the notation just a bit to this for the sole purpose of just emphasizing the Boolean valued function. You don't have to do it in your homework, but just extra emphasis on the notes. So down below, we'll do the proof. One extra thing we need to see it all for the proof is the original definition of the sequence. So let's grab that as well. Okay, let's see what we've got. We've got the statement we're going to prove. We've got the method we're about to use. Here's the statement. And here is the actual statement itself we're proving. Let's begin by saying base case. And the base case, we want to prove down here, as we said it, that P of 1 itself is true. So let's just begin by defining an integer. Let n be greater than or equal to 1, be an integer. Next thing we can do is say, well, look into the statement of what Pn is saying. It's saying an equals n squared. We need to check if this is true or false. And then once we find the Boolean value, we'll just map it this way. So let's start just like we always do on the last section, left-hand side first. If n is greater than or equal to 1, then a1, that's a supplied value, it equals 1. And we're checking this statement. So we go to the right-hand side now, plug in the value 1. 1 squared equals 1. Now we're checking the equality, but we outputted 1 here, we outputted 1 here, so equality does check as true. And so that's what we say next. This shows P of 1 equals true as required. Now we're ready for the next step, the inductive case. Any questions at all, folks, with the base case? Okay, just trying to get some of my screenshots in a good line here. Now for the next case, we're doing inductive case. On the inductive case, wherever you started, it could be 0, that's when you're copying this information to the letter. It could be 5 or 1 like in this problem. Just go to one integer higher. We'll say let n be greater than or equal to true, then 2 rather, and assume that we're now looking at this statement down below is true. So let's say assume that P of 1 and P of 2, up to you how many extra symbols you'd want to put in here. You might say P of 3 or just go simply and. Our author didn't put in this one, we just threw it in after the fact, but for the law of proofs we're doing in this document, this is something that comes up. So it's good to get the prior term even before the n-1 term. So let's say and Pn-1, excuse me, n-2, and Pn-1 is true. Because of all of the and symbols, this is one big conjunctive statement. When we assumed it's true, that means we assumed every single one of these predicate valued functions here is true as well. We'll just use the parts we actually need to do the next step. And what is the next step? It's this part. We have to prove that the next value for the predicate function P of n evaluates to true as well. If we can do that, all of our work here is complete. So let's say what our goal is. We must show P of n equals true. So what was P of n again? It was that statement down below. And so if we can get that equation to check as true, we are done. We start this off slightly different in a certain sense. When it was the base case, we had a specific integer at 1, so we just plugged it in on the left-hand side. The right-hand side, we observed it, checked as true, and then we're done. For the inductive case, we're going to start on the left-hand side, do a whole bunch of algebra with the goal of emerging as n squared on the right-hand side. So now we're just pushing through a big equation, essentially. So start on the far left, an equals, and remind yourself, how do you calculate an? You go up here. This is how the sequence itself was defined recursively. This is valid for n greater than or equal to 3. Let's see here. Do we need to make an adjustment then? What if n was 2 itself? We allowed that here. You know what? We might have an extra adjustment we have to make. And thanks for the person mentioning it earlier. That is a valid concern in this structure right here. You cannot pass 2 to that whatsoever. We've got a problem. We need to fix this little loophole right here. If I can't plug in 2, what we can do is, let's check P of 2 specifically right up here. If we can check P of 2 is true as well, we can bump that up to 3. And that means if this is 3, we can use the formula down here that we really need to use actually for an. So being extra careful with the proof sometimes is annoying. Sorry if you're working in pen. Add a little bit of extra space here, and let's go to the next part. Now let n equal 1. Hang on, I'm just noticing here, that should have been equals 1 up there. I want it to be 2 up there. I'm going to blame this on the work meeting. So I should have said equal to 1, not greater than or equal to 1. We use specifically 1 itself. We put that in purple just to signify that's a correction that we had to make. Now at n equals 2, Let's circle that part as well. We'll box it out. We need to check that the predicate function here that we defined really matches out or outputs a true, but not so bad, right? We could say A2. Let's say that A2 equals is provided for us to kickstart the recursive structure 4, and come down here, the right-hand side, n squared becomes 2 squared equals 4. This shows P of 2 evaluates to true as well. Now, because this is only valid at n equals 3, this was a required step, kind of a surprise as well. Let's actually bake this into the comment as well, because I think that's easy to miss. I definitely missed it until I looked again and recalled the earlier comment in class. So let's say here, because the formula for AN is only valid for n greater than or equal to, let me try again, 3, we must show P of 1 equals P of 2 equals true in the base case. Extra tricky problem just out of nowhere with these kind of things. Does that make sense, folks, with the adjustment we had to make, the additional comment?
Wouldn't you want to say P of 1 and P of 2 equals true instead of equals each other?
Yeah, that's kind of a weird way to say it, right? The thought of that was saying if f of 1 is 3, f of 2 is 3, you can compactify the whole statement as f of 1 equals f of 2 equals 3. That was the kind of thought there, but I like your idea because this is not an easy function to think about, right? It's Boolean valued. If you're really careful with how it evaluates, it's a great reminder in this case. So let's actually make that adjustment here. P of 1 equals true. And P of 2 equals true as well. In the base case. Other questions or comments so far? Okay, so far with this exciting problem, we made a conjecture. We had to readjust our base case, and that's required because now we can come over here, make a very, very critical adjustment. That 2 is now a 3. And I think that deserves that extra special color right here. It's not only a correction, it's a big correction, and it's a required one to kickstart this formula. Now we're back on track. If we're going to prove P of n is true, we're using all of these assumptions that they are true, and we checked P of 1, P of 2 specifically. So next, for AN, this could be a 3, but this works for any integer greater than or equal to 3 whatsoever. We can use this structure because of its greater than or equal to 3 matching up and just write out 2 times AN minus 1 minus AN minus 2 plus 2. So we got a step down. We're ready to proceed to the next steps. This one doesn't take too much algebra, but this is the key step right here. We made a whole lot of assumptions in the inductive case that every one of these statements from the predicate P of n is actually true. And now we're trying to show that P of n is true, that AN itself is going to evaluate to n squared. That's our target. But we have information on AN minus 1. Information on AN minus 1 is captured here the moment we said Pn minus 1 is true. So let's just read it out. Pn minus 1 equals true directly now implies, come down here and just rewrite the formula for Pn minus 1. all we're doing is changing the index here and the base on the right-hand side. So an minus 1 is now n minus 1 squared. We'll just dump that into that location. This is more explicitly showing, finally, this is why we needed strong induction. We need this statement right here as well. So take the Pn minus 2 statement, kind of just do some extra parallelism right here. Pn minus 2 is true. We'll now directly imply an minus 2 is n minus 2 squared. So we're set up for two big substitutions. An is now equal to 2. In this position, for substitution, put in n minus 1 squared minus next substitution in this position, we have n minus 2 squared plus 2. So that's an, and if we're on the right track, if we didn't make any mistakes, if our conjecture was correct, and remember that's critical too, we've got the right structure here, then all of this algebra should coalesce to an n squared. This is the point at which we just start cranking it out. So an, I'm going to just write one big line and hopefully get to n squared. Starting with squaring out to this group, it becomes 2 n squared minus 2n plus 1. Square of this group over here is n squared minus 4n plus 4. Actually, let's save some vertical space and continue horizontally. Distributions now give us 2n squared minus 4n plus 2 minus n squared plus 4n minus 4 plus 2. And let's check our cancellations on this. We've got cancellations on the negative 4n's and positive 4n. The constant terms also cancel out. That leaves us with 2n squared minus n squared. But then that means an equals n squared upon combining those like terms. But that's what Pn is saying as a statement. An is n squared. This directly tells us Pn as a Boolean valued function is now true. And how did we get to there? We assumed all of these cases are true after proving two base cases. If we assume all those are true, they're leveraged to show finally the next case is true, Pn itself. So we did this part right here, Pn is true. Essentially what we've done is proved one gigantic implication, that the assumption of this whole left-hand side in the implication is true, implies the next one is true. But then that implication implies for all n, P of n is just always true outright. So that's our conclusion of strong induction. We just have to wrap it up. We can say very briefly if we like, the proof is now complete. We've shown pre-n true. Or you could be really fancy. You could say, therefore, there's always a stylistic choice to end your proof. So you've got to end it somehow. You could say P of 1, and let's put a bracket here, P of 2, and Pn minus 2, and Pn minus 1 implies Pn as required. So that tells us we have a completed proof. It really is the case that for this recursive sequence by the red dot, it can be defined just by giving the nth term as n squared. It could be defined other ways. We saw other potential patterns for sure, but it looks like this one might have been the easier one to prove in the end of the day. Any questions at all, folks, for any elements of this proof?
I think you accidentally did equals instead of implies in that last line you just.
Oh, good call on that. That one is a critical error right at the last step. Implies makes that flow a lot better. Thanks for spotting that one. Other questions at the moment or corrections? Okay, so that's how a conjecture problem goes. I do have a conjecture problem kind of like this in the homework as well. So when you go to do this problem, In the 5.2 homework, here's how it looks. That's the wrong one. In the 5.3 homework, when you go to do the related problem, here's what it looks like. So we have a recursive sequence. The starting values are 2, 6. Formula is similar to ours, slightly different rearrangement, starting at n equals 3. We'll conjecture a formula just like we did, prove it using strong induction. But this is just our very first time doing something like that in this class. So if you get stuck, I'm very, very happy to help out. In fact, if you want to ask about it at the start of class after spring break, something like that, that could be a good just refresher on this kind of work. So this is not a problem I'm going to bring to exams. Conjecture work is creative work. You need extra time and low stress to do that kind of stuff. But it's a fun one to do in the homework setting. So it'll come up in only these kind of contexts. So we've got a good proof down. Let's eliminate some of these elements that were just here for reference. Geez, that's a lot of stuff here. And here's our next problem to try. Another infinite sequence. And this time we have A1 is 3, A2 is 5. Recursively we're defining all prior terms after that using this structure. But I'm not going to give us a whole bunch of conjecture problems. That can get kind of tiresome after a while. In this problem, we're going to say directly that the nth term can be defined in this way. It's just powers of 2 plus 1, kind of odd. There is no way I would have thought of that by looking at the recursive structure here, that it just collapses to this formula. Just like in the last problem, recursion is kind of weird. The structure it takes when you write it down versus if you can get it down to an nth term formula always look wildly different. So we'll start off this one just focusing on the strong induction. Then on part B, we'll implement it, show what the pseudocode would look like if you were really trying to define this somehow and execute the terms in that code. So first, before we even try to implement something, we would want to know if it is implementing it correctly right here as a function. 2n, an equals 2n plus 1. Then just for the fun of it, we'll implement the recursive function right here. Even though that one would be a little bit easier, seeing how this goes with recursion and pseudocode is also a pretty great way to learn about recursion in the first place. So let's give this a try. We have a statement to prove. For all integers n greater than or equal to 1, we have that statement. I feel like there's no harm at all just launching right into the proof right here, right now. In every proof that we've given, I've always included a little bit of extra information, maybe a predicate function like we've been doing, something quantified. That's just to help organize the thoughts. If it's valuable to you, I'd suggest that's a good thing to do each and every time. But if it seems like it's not helping you at all, that you're confident just jumping into the proof, that's okay as well if you decide to work that way. So if I was going to write out and quantify what we're proving, I'd probably begin by saying, we have a statement, P of n, that goes an equals 2 to the power of n plus 1. Then I would say next, we will show. In place of show, you can say we will verify, we will prove, anything along those lines are all saying the same thing. We will show that for all n in z greater than or equal to 1, so we're specifically saying integers n in this way, the statement P of n is true. Again, you can leave it just like that. That's a really compact way to say all this, but if you really want to emphasize the Boolean function, you could write it this way as well. P of n evaluates to true is kind of being a little redundant here, but it's explicitly saying what we're going for. Like before, we have a base case, and like before, we have to be mindful that this formula here for the nth terms in recursion only starts at 3. So this tells us our base case should be verifying both A1 and A2 at the same time fit within this formula. So let's say let n equals 1. Then over here, we're checking the predicate function P of 1. So on the left-hand side, we have an equals. This is a direct lookup, value is 3. And AN is a bit awkward. Let me say A1 is 3, better said. And go to the right-hand side, just plug in the index of 1 in the right-hand side's formula to get 2 power 1 plus 1. And it's definitely 3. So this shows P of 1 evaluates to true. We just have to do it all over again. So update the index to 2. Do the same check as before. Here we have 5. We'll say then A2 equals 5. And that was the left-hand side here. Index is 2, so go 2 power 2 plus 1. But that is 5, so we have 5 as well, matching out. This shows our statement here, when we plugged in 2, does check out as true. In other words, P of 2 equals true. And in this whole proof, there's one thing I wish I would have said, but I forgot to say it. I never said base case. I'm not sure if I can fix this too easily. Let me see if I can do it by just slightly cheating. Let me see here. I'm going to rewrite my proof statement up here. And then below, I'll just say base case. I'm not picky when I grade your work on whether you said base case or not. But it's kind of like writing out code. Sometimes you want to break things down so it's readable, add little comments to direct people what you're doing next. And this is a pretty major comment because it's reminding us of the structure of the actual proof method we're using. Well, we've got our base case down. Our base case was really P of 1, P of 2. And so now over here, we'll go P of 1, P of true, all the way through, or all assumed true in the inductive case. Any questions at all, folks, before the next step? Okay, here's that inductive case. In the inductive case, again, it pays to be really, really mindful of what the next integer will be. Because we took care of 1 and 2, we'll say let n be any integer greater, n greater than or equal to 3, be an integer. Then it allows this formula to work normally with what, we see up here. Let's carry this down as well. Okay, so we took n to be an integer. I have all the statements we're working on proving down below. N is greater or equal to 3. And assume, let's say this slightly differently. You could just say assume that whole structure is true, or you can say this differently. It's all up to you. Assume P of 0, comma, P of 1, comma, P of 2, all the way through, Pn minus 2. Oh, hang on. That almost looked right to me, but I keep on forgetting. We're starting at 1. Let me start over here. Starting over again, that down below is meant to help me. Let's assume P of 1, comma, P of 2, comma, P of 3, through P n minus 2, comma, P n minus 1 are all true. So pick your favorite way to say it. You have to say it some way somehow. And there's even more compact ways to say this if you're curious. For the folks that like to say this as compactly as possible, you could just simply say, assume Pi equals true for I in 1, 2, n minus 1. Something like that would be a really compact way to say it if you prefer as well. So this is just another option. That's why it's in orange. Now we can say what we're really trying to show. We're trying to get down to that statement there, P of n. So let's say we must show P of n is true. But we have a pretty good idea of how to do this. If you're trying to show P of n is true, you just go down to the predicate function, whatever it is. It tells us we need to verify that equation must be true with all of our prior assumptions in the inductive case, but we can only start on the left-hand side, an. Then we take a really, really careful look at the integer. It's starting off at 3. So we are allowed now to use this whole formula for an. An is going to be equal to 3 times an minus 1 minus 2 times an minus 2. But for both of these values, an minus 1, an minus 2, they're involved here and here, just like on the last problem. So that means if we'd like, we could just read out those statements just to help out on the right. I'll say Pn minus 2 equals true, implies, come down here and just change the value of n. An minus 2 equals 2 to the power n minus 2 plus 1. And then from this statement, Pn minus 1 equals true, implies a n minus 1 equals 2 power n minus 1 plus 1. Once we wrote it down once, for any change of the input here, just use the parallelism you see above and below to write it down twice. So we can now make some substitutions. These two values go in the right spots in the right order, so be mindful of the substitution as well. An equals 3 times an minus 1. I have regrets on how I wrote this out. This looks like it was designed to trick me. An minus 1 is the statement below, 2n minus 1 plus 1. Minus 2 times an minus 2 is this statement above, 2n minus 2 plus 1. Now we're at that one spot in just about every inductive proof that we've done where it's all algebra from here. And in our algebra, the strategy is to keep your eye on the goal. Get to 2n to the power of n plus 1. I don't know how we're going to do that. This is kind of a weird structure. But if the statement here was true at the very beginning, that statement, there's got to be a way to do this. So let's see what algebra gets involved. On next line, probably the best way to get to the next steps is just start distributing. I have 3 times 2n minus 1 plus 3. And then from here, it's going to be minus 2 times 2n minus 2 minus 2. So this is the same formula, but now expanded. I can't combine bases over here, so I'm stuck. We can combine bases on this one. That might be helpful. And another way we're stuck is that this term and this term, as written, let me capture the negative sign just so that doesn't feel weird. Those two terms as written are not like terms. We can't combine them at all. But if we do some exponent work here, the power does become n minus 1, and they do become like terms. That looks like it's the only way forward, but also notice with the plus 3 and the minus 2, we've got that part at least. The plus 1 part is satisfied. So this kind of informs us on our next step. To get 2 power of n in one spot, let's combine the bases over here. So this will turn into 3 times 2n minus 1. Combine the constants, I have now plus 1 minus, over here it's 2 times n minus 1. We bump the power just by 1 when we include the extra factor of that base 2. At this stage, these are like terms altogether. We have 3 copies of n minus 1, take away 2 of them. That just means we have, let me say that better. The coefficient here is a 1, not a 2. So 3 copies of that, subtract 1 copy of 2n minus 1, gives us, let me just fix that bit right there, gives us 2 copies of 2 power n minus 1. I had to think about again on how to combine like terms. The coefficient here I was looking at as a 2 versus that 3, which is not right. The coefficient is -1 for the structure 2 power n minus 1. Now that we're here, we're basically there, right? We just need to combine the base 2's one more time. We have 2 to the power of n plus 1 as required. Why was it required? It's because we said up here on this block, we must show Pn is true. We started at an, and we emerged with 2 to the power of n plus 1. That is the statement Pn, and so we have verified it true right at that step. Now that we got to that step, our proof is pretty much complete. We just need to tie it off somehow, conclude the actual proof. But any questions at the moment, folks? Getting through any of those steps? Okay, let's make a statement. We said we're doing a proof. We never said what the method was. It might have been nice to say proof by strong induction, something like that. But since we missed that, let's say it down here. This completes the proof. Using strong induction. And some people might have ended the proof right here because you did conclude. You found the thing you need to find as required. Requirements are all fulfilled. If you ended it right here, it does feel kind of terse, but that'd be appropriate as well, I'd say. But we did it, folks. This one was kind of nice because it gave us the formula to navigate through this recursion right here. All we had to do is prove it's true right away. Strong induction is a great tool because of the information on the right. We needed 2 prior cases to get to the nth case to show it's true. Well, we'll do a part B on this one, but any questions or comments at all so far? Okay, so here's the part B finally. Just trying to see what I can eliminate here to clean this part up. Part B says, write pseudocode that implements a function which returns the nth term of the sequence, then execute this code using the programming language of your choice. And it's a kind of a silly question in a way because 2 ways to do this. You can either use the recursive structure that was originally provided, or we just proved something. You could give pseudocode that just uses that. So as the question is written, you have options. Either way you'd like to do it will be just fine. Let's use both options just for the sake of practice on this. I think the fun one might be using what we just derived, and the interesting one is recursion. So let's say method 1 versus method 2. I feel like this needs a new page just for the sake of making sure we aren't cramming it in. So in method 1, we need to define a function, and depending on the language you use, the structures kind of vary a little bit. Some structures put function first, other structures put the name of your function first. And this is just a generic sequence, so I'd probably start off my pseudocode by writing just seq for sequence. It will be equal to a function structure. I'll put here in the pseudocode the actual input to the function n. Other languages might want it right here when you define the function. All just depends on what language you're really using. But the idea of pseudocode is if you write it down once, we should be able to put enough detail right here that you can make the right adjustments to adapt this to any language you're actually using. So I'll begin saying this, put in a block where I'm going to end a block and say return something. And what do we return? Well, if we pass n to this function and want to use this structure, we would just say return to the power of n plus 1. And now our work is complete. We don't need to do anything further on. So that's kind of valuable in a certain sense, right? Once we had the formula for the nth term, implementing all the terms of the function, or excuse me, all the terms of the sequence as a function that outputs them is really, really rapid. Now, method 2, here we're going to say using recursion. We did this once with the factorial function, but there's a little bit more going on with the recursion here on how this one's defined. So it's a little bit more built up on this end over here. But first, any questions with method 1? Okay, so now for method 2, let's call this sequence if you prefer, or if you're implementing both just to see the difference, maybe you'll call it sequence underscore 2, something like that. I'll imagine we're only implementing one and executing it, so I'll just give it the same name. Sequence equals function. And it's good to say somewhere what the inputs to that function would be, what its arguments are. So I'll put it right here before I forget. Put in a little curly brace. And what do we return this time? It depends on cases, right? If n is 1, this is what we would return. If n is 2, this is what we would return. So let's say if we need to do a comparison check on what n is. So say if n is identically equal to 1, return something. We just want to give it back 3. So return 3. But now this is a kind of a trichotomy, right? There's a middle case. So what we say here is, depending on the language you work on, I'll go else if some other condition occurs. The index n is identically equal to 2. And as a comparison check equals 2. If this comes out as true, we'll go and return that value, 5. Then, if neither one of those conditions are true, we'll just say else without the if to say this is the third condition and final one. Else return. Let me get some extra space in there. We want to return 3 times the n-1 sequence term, which means we can call the same function we're working on right up here. Take 3 times sequence, pass to it n-1, which means it has to go through here, check where we're at. If we get one of these values, we'll return it right here and do a multiplication just right here. Then it's going to be -2 times sequence n-2, close that parenthesis, and that should do the job for us. So method 2, if we don't use the proof that we laid out down below and just use the recursive structure as is, looks like this. And one thing I didn't mention when we tried this with the factorial function is there is no error checking inside here whatsoever. So when you go to actually use this, you might get a Stack Overflow like just immediately if you put in the wrong value. But if you stick to integers and you don't throw in a 0 or a 0.3, something wild like that, it should work as expected. Any questions at all, folks, on the pseudocode before we test it out? Okay, let's give this a try. When you go to do the pseudocode in your homework, I'm not going to be really hyper picky on how I grade these things. It's more about to just give it a try. If you don't have a ton of coding experience in your background, don't hesitate to reach out and ask for help. Anything involving pseudocode, I'm very happy to be very helpful on, even on a homework assignment. So actually implementing this stuff, should be pretty exciting. Let's start with the method one function over here on the left. I'll actually do what I suggested before and call this the sequence function one, since we'll give two definitions for this. Sequence one, in the environment I'm using, I use left arrow for an assignment, like this assignment here. Function, n and then curly brace. Return is just saying, after we give some value to the function, what will it output? And now we're using the whole formula that we proved. Return 2 power n plus 1. And again, with this function, no error checking whatsoever, so it either works or it doesn't. And even if it does work, you better give it the right input, or else we're going to have some problems. Let's see if it does in fact work. Let's check it on 1. Sequence definition 1 on 1 gives us 3 as expected. Sequence 1 on input 2 had better give us a 5, and we've got it. Let's try it one more on 3. On 3, we get a 9. We'll use that as a double check where we go to check out this other method over here. But that's a pretty fast implementation. And again, by the way I worded this problem right here, I didn't say which way to implement pseudocode. So even on the homework assignment, you have options. Either use what you proved or use the original thing. Either way would be just fine. The second one, let's use this structure. I want to go down just to get some extra space for us. I'll call this one sequence 2. Gets function, structure. The argument is just going to be n as before. And now we have 3 cases we want to maneuver through. So let's write out if n is identically 1, return 3. Else if, let me format this a little bit better just in case I make a mistake. That might help me find the mistake. Else if n identically equal to 2, return 5. So we're just encapsulating the starting terms of that sequence. Actually, I'm going to take that back. I'm running out of space. I'll just compact these again. And last one is else n. Well, we don't want to put a condition right here. This is just else. In other words, any other value that's not 1 or 2 is going to qualify. So we just put down below return. Here we need to be a little bit careful. 3 times sequence 2, because that's the function we're defining up here, at n minus 1, minus 2 times sequence 2 at n minus 2. That should do it for us. But with a lot of things like this, we definitely want to double check it to see if it's working out. But there's sequence 2 now defined. So if we go to output some values, sequence 2 at 1 gives us the 3, so that's encouraging. But it should, right? If we pass to this integer 1, it executes this block returning 3. We're just checking if it really does that by the way we implemented it here in this language. Another check, sequence at 2. Sequence 2 at 2 does in fact return the 5. And just a reminder, let's say, actually, let's do a whole new test. Sequence 1 at something large like 30. Sequence 1 is referring to this definition here. It outputs a really large number. That was, well, we can still work with that. Let's try this function, which we called sequence 2 above. Sequence 2 at 30 is, it took it a moment. I don't know if you noticed that. Let me rewrite it again. Look for a little thing right above the red dot. It kind of flashes there like a subliminal message. But because this is a recursively defined function, there was a lot of computation here. It had to run through what happens at 30 by recursively going through this definition here. A lot of computation, but double checking, they're outputting the same values. Just for fun, let's see how it takes sequence 2 at 300. It's working on it. And now we see the value on trying to conjecture these kinds of formulas and actually proving them. If there was something about this process that really corresponds to the physical reality, that was an incredible formula to have down below right there. Because this is going to take a while. That button is actually a stop button, just in case we are deciding to abort the whole run. Let's see how the computer is handling this. Not too bad. Doesn't look like R is really diverting a whole lot of resources from the system memory or CPU, but still, this might not complete on us. But any last questions, folks? Either writing down the pseudocode or implementing it? Okay, again, that's going to take a while. And that's kind of the motivation of the next problem down below. We'll look into this after we come back from spring break. This is the good old Fibonacci sequence. This did come into be from an applied problem. Fibonacci was looking into just dealing with rabbit husbandry, the breeding of rabbits, and this sequence right here, for the short run, does capture the amount of rabbits you get after each season. So this one is an interesting applied problem. We're going to implement it like this as a recursive function. We'll prove that it's actually going to execute correctly. And then if we have the energy, we might discuss what is the formula for the end term, because these things, they take a while. There's value in discovering better ways to compute this kind of stuff. But I think this is a good stopping point for us. We've worked pretty hard. We are almost done with strong induction. When we come back from the break, we'll have the opportunity to refresh on this with one more problem before moving into the other topics. But any last questions or comments, folks, before we call it a night? Okay, have a great one. I'm probably going to have to terminate this one, but if it actually runs through, I'll let you know what the output comes out as. Have a great night, folks, and I'll see you folks after the spring break.